Welcome back to che531. In this video, I'll be talking about trust region method. In the last video, we talked about steepest descent method, where we set the direction to be the steepest descent, and we try to find the optimum step size, lambda. We found that in steepest descent, the path follows a zigzag route, and that is actually not really optimum. In trust region, however, we want to improve that path and basically not following a zigzag path. On top of that, instead of fixing the direction and changing or searching for step size, we're going to fix the step size and change for the direction. So it's basically sort of opposite of steepest descent method. Okay, so imagine we have a function and we want to find the minimum, or basically solve for unconstant optimization using trust region. So in trust region, we assume that we fix the step size lambda, or in other words delta in this case. So we're going to fix the length along the minimum path to be delta, and then search for the direction r. Okay? So instead of using the function directly, we're going to use a Taylor series version of the function, okay, to find the direction r. So if you use the Taylor series for function f, then our g, which is going to be the Taylor series of f up to maybe the first three terms, is going to be our Taylor series of for function x and for function f at about point xk with increment of r. It's going to be the function f itself at point xk, and then the change in xk, which is r, times the gradient of f. So that's the second term in Taylor series, and then plus 1/2 of the change r transposed and then times r. Now you see that because these are vectors, we have to really think about the right position when we do the multiplication. Okay, so r transpose r, and then the second derivative of f, which is called Hessian Matrix. This is pretty much like in one-dimensional Taylor series, if you remember from high school, that any function can be written as, let's say, f at point xk plus the first derivative of f times the change in x, which is called, let's say, delta x or r, and then 1/2 of the change raised to the second power, so we have r times r, and then times the second derivative of f, which is now Hessian in vector form. Okay, so then how we can measure whether the step size that we're taking along the direction is enough. So now we have two functions to look at. One is the original function f, and the other one is the Taylor series version of the original, which is called g. Okay. So in the Taylor series, we only keep the first three terms. Now, at every step, we're going to look at the change in the function itself due to the change in x value divided by the change in the Taylor series version of the function for the same step size, or for the same step direction rk. So in the numerator of this ratio, right, the numerator is the real or actual decrease of a function. In the denominator, that is the decrease in the Taylor series version. Okay, so now we're going to look at this ratio. If this ratio is bigger than some predefined value, let's say mu, okay, that means the change in the real function is more than expected. And if the reduction in f is more than expected, then we're going to keep that step size. So the step size is good. So we're going to accept the step size. Otherwise, we're going to change the step size and lower the step size, because if the increase in the function is not as expected, that means maybe the step size is too large, so then we have to make it smaller. If the change is bigger than expected, that means the direction is good and the step size may not be even enough, so we make it even longer. Okay? All right. So now the condition turns out to be like this. We're going to pick two numbers, nu bigger than mu. So these are user-defined numbers. And every step we're going to look at this ratio. If this ratio is bigger than nu, okay, then we're going to increase the step size. And if this ratio is less than mu, we're going to lower the step size. Okay, so again, if the ratio is rho k is bigger than nu, then we increase the step size, and if the rho sub k is less than mu, we're going to lower the step size. Okay, and so here's the pseudocode. Pseudocode means something that is similar to code, but not really. We are not really writing the MATLAB commands yet. Okay, so we're going to start with step 1, and we're going to set the limit for the step size delta. Okay, so this is trust region. We have to set the step size and find for the direction. So we set the step size to be delta bar. Okay, now we're going to look at the modified version of the function, or the Taylor series version of the function, and search for the direction r, such that the norm of r is less than delta. Okay, after we find r, we're going to test that ratio rho k. If rho k is bigger than nu, then we're going to increase the step size. We're going to double it. Okay, but we don't want to go more than some predefined maximum delta bar, because you don't want the step size to be unlimited. So anyways, if rho k is bigger than nu, we're going to double it. If rho k is less than mu, then we're going to halve the step size. So step size is lowered by a factor of 2. Okay. Once we fix the step size, then we're going to go and look for the direction r using the Taylor series version of the function. So in here, we're going to use steepest descent. Okay. All right. After we find the direction, then we can update the x value. So it's going to be the current x plus the change using the direction we found and the step size, and that gives us the next x value. And we're going to reiterate until the difference between the two x values are small. Okay. So there's one question here, and that is these numbers that we talked about, 1/2, like halving the step size or doubling the step size. These coefficients, 2 and 1/2, these are user-defined. These are not really part of the method. Okay, so the user actually can define these even before starting the minimization. Okay, so now steepest descent follows the zigzag pattern, but in trust region we should not actually see that zigzag pattern, and actually it's more efficient than the steepest descent. However, trust region also comes with different flavors. One of them is called Dogleg Method, which we're going to talk about in a minute. So in Dogleg Method, which is also a note in the lecture notes on page 90, so we're going to start with Taylor series of function f. So let's say my f is written in the form of a Taylor series. So this is the function at point xk, and then this is the gradient of the function, plus 1/2 of the change in x times the second derivative of f, and then times the change. So this is basically delta x squared times the second derivative of f. and this is just the first derivative of f. Okay, so now in the simplest form, we can say instead of minimizing f, we're going to minimize only these three terms. Let's say we change our f approximately to these three terms. And to minimize the f, we're going to minimize basically this, which is fk, plus the gradient, which is gk, times the change in x, which is delta x, or we call it p vector. Okay, and then 1/2 of, this is p actually, 1/2 of p transpose, and then the second derivative times p. Okay. Now the question is how we go about finding p. So we're going to talk about that in a minute, but let's say after we find p, we have to check whether the step size is large enough. So we're going to find that ratio same as we discussed before, and we find the change in the function divided by the change in the Taylor series version of the function, which is right here. If this ratio is bigger than something, then we can increase the step size. If it's less than some other thing, then we have to lower the step size. Now in Dogleg method, we pick two numbers here, the lower and upper bound for the delta. So let's say we choose the lower bound to be 0.25 and then the upper bound will be 0.75. If this ratio is less than the lower bound, that means the step size is too big, right? That means we are not making enough, or we're not making a big change in the function, or we are not reducing the function enough. Okay, so then we're going to lower the step size. In the new step size, or for the new step size, we're going to have, let's say, 1/4. That's the coefficient 0.25, right? 1/4 of the step size, 1/4 of the current step size. Okay. Now, on the other hand, if the ratio is bigger than the second number 802, that means we are making really good progress and the function is reducing a lot. So we're gonna basically double the step size. Okay. So this 1/4 and 2, these are again user-defined parameters as mentioned here and here. So this is where we have to reduce the step size if the ratio is less than this. And here is where we increase the step size if the ratio is bigger than the second number here. If none of these happens, then we're going to keep the step size as before. So we're not going to change the step size. Okay? Alright, now, so we talked about the step size a lot, but we haven't talked about the direction yet. So at every step, we're going to define two directions. One is the steepest descent direction, and one is the Newton's direction. In the steepest descent direction, we have the gradient. We get the norm of the gradient divided by the gradient times the Hessian times the gradient. Okay, so this is going to be, and then basically, okay, we times this gradient again. So this whole thing would be normalized direction along the steepest descent, because this is along the gradient already. And this is basically just a normalization. In the Newton's method, we're going to basically solve it using Newton's method. So in one step, using one-step Newton method, we're going to find the direction, which is going to be along the tangent to the function. So this is nothing but the tangent direction. And this thing is the steepest descent direction. So at every step, we're going to basically choose one or the other, or basically a mixing of the two. So there are three options here: either choose the steepest descent direction, choose the Newton's direction, or choose the combination of Newton method and Newton direction and steepest descent direction. Okay, so in the next part we're going to talk about when we have to choose the steepest descent or Newton's direction. So stay tuned for the next part.